Медведь. С видео.
Ген, микрофон.
Okay, hello everyone. Once again, nice to see you. We will start in a minute. Okay, it's ready on my side, and I think everyone who wanted to come has joined us. So once again, hello everyone who has joined.
Hello.
So today we're going to continue discussing complex numbers. So we've discussed general things about fields with no details because all those details belong to another course. And we are not going to really have much things about fields in the course or in the test or whatever. Everything, again, about fields belongs to the course of abstract algebra. Why we wanted to talk about them is because we want to discuss a particular field that is the field of complex numbers. So today, wait, okay, it writes. Today we want to discuss complex numbers. And I remind you that they have some abstract hard definition using pairs of numbers like AB, but it is not very nice to use this notation in practice, and no one does that. Instead, everyone writes them in this way. We write them as numbers of the form a plus bi, where I is a special constant, some special number, such that the following rules are satisfied. The rule of addition is as follows. Two such things are added component-wise, a plus c separately and b plus d separately. This part of a complex number is called its real part. And this part is called imaginary part. Well, but again, let me remind you, I'm sure the lecture told you already, but let me remind you that the word imaginary doesn't mean that they don't exist or something. It is a historical word. people have invented them like 6 or 7 centuries ago. And in those times, they believed they don't exist. They are some stupid construct to solve equations, etc. But later, people understood that complex numbers are in fact quite real. Well, and that many things in nature well, kind of work on complex numbers. For example, one of the most modern branches of physics, quantum mechanics, works entirely on complex numbers. So it kind of assumes that in fact, in our world, everything inside works on complex numbers, but they somehow disappear after some special kinds of operations, and in like to our ways of viewing the reality, we only see like real numbers in some sense. Again, I'm oversimplifying things that I myself don't understand very good, so maybe you should have take my words with like a grain of salt, but still, in some sense, modern physics works on complex numbers, not real numbers, at least in some parts. Okay, that's enough of like advertisements. So complex numbers are very interesting, but still, how to use them? So there is operation of addition, and there is operation of multiplication, which works as follows. You simply open all the brackets like you would with usual numbers if you obtain some complicated expression like this. So the result is AC plus BCI plus ADI plus BDI squared. Here, when I multiplied BI by C, I changed the order because it is customary that I stands the last. Likewise, if I would have something like BX, and here I would have C plus something, then in the result, I would write BCX, right? Not BXC, because X is the variable here, and it kind of stands on a separate place. So something like this happens here. Again, it is not important. It is just the way people write it. So this expression is wonderful, but it is not of this form. Complex numbers have two parts, real part and imaginary part. But this number has three parts, real part, imaginary part, this one, let me underline it, because this plus this together is some number we can add BC and AD together and get some number by I. And also this weird part that has I squared. But there is a special rule that says what I squared is equal to. And the rule is as follows. I squared is minus 1. This is the reason why we invented complex numbers. In real numbers, there was no number whose square was minus 1. We lacked such a number. It didn't exist. And that was a problem for some reasons. So we have invented an artificial number that, well, fills this gap. And then again, experiments show that in fact, we have not like invented those numbers, but rather discovered them. In fact, everything works using them. So
we should not, this is some kind of proof?
Proof of what?
Of this fact, like I squared is equals to minus 1.
No, that is the definition of I.
I see.
We consider a special object I such that the rule of working with it are as follows. When we add something, it works like this. And when we multiply, it works like this, where I squared is minus 1. So we can rewrite it as AC minus BD plus BC plus AD times I. BDI squared gets turned into minus BD.
I'm curious just that, do we have such, could be such, for example, field where I squared could be a -1 and also 1?
That's a good question. So after we have invented such an addition and multiplication, we have to show that they have some nice properties, that the resulting object is good enough for us to consider. If it would be something not satisfying usual rules, it would be useless to us. So in this case, we check 8 properties and verify that the result is a field. I won't do this. I hope this was done in the lecture, at least partially. Maybe some of the properties were checked. But if you put 1 here, for example, you will see that some of the properties won't be satisfied, in fact. So you won't obtain a field. Again, it's not obvious. You have to do some checks to understand this. But like, in fact, if you put a positive number here, there will the fact that there already exists the number whose square is this number you have will somehow make it so that there is a contradiction. Again, it is not obvious, but it can be shown that there will be a contradiction. And if you take another negative number here, then it will work. But again, the tradition is that I squared is -1, not something else.
I see. Thank you.
Any other questions? So again, we can, when we're doing like problems, we can ignore the complex situation, how the complex numbers were defined in the lecture using pairs, and we can ignore everything and simply follow the simple rules of dealing with them, how to deal with sums and how to deal with products. The rules themselves are extremely easy. You have to open all the brackets you see, and you have to remember that I squared is -1, nothing else.
So you'll have a bit opposite situation, like when we, for example, have a -1 and get squared, then we get just a usual one. But in this case, we will have 1.
Yeah, this is still true. Nothing changed.
No, I know that's nothing changed, but we, if talking about complex numbers, what we get, like I not squared, then I squared, then I in cube, and then I in fourth.
What is I cubed? Well, I
Yes.
cubed is I squared times I, which is -1 times I, so it is -I.
Oh.
I to the 4th power is I squared times I squared. That is -1 times -1, so it is 1. Or alternatively, it is I cubed times I, which is -I times I, which is -I squared, which is -1, that is 1. Again, it might be not obvious, for example, that if I compute it like this, or if I compute it like this, I obtain the same result. But if you show that all the properties of the field are satisfied, then automatically, no matter which way we compute, we get the same result. So it makes sense to write like this.
That's quite interesting. Just that only square, like only for the even power, when we have a square, then we get this -1.
Okay, I'm not sure how much interesting that is, but well, it is obviously.
Just because you think that should be the same for the even powers, but actually not.
Okay, yes. So next time we're going to talk in details about finding powers of complex numbers, but today we won't reach this moment yet. So, well, before we go on, so let me now take one simple expression and simplify it. I want to simplify an expression by using those rules we've discussed. So it goes as follows. When I take this expression and open the brackets, I obtain 2 times 3 plus 3 times I. So I could write I times 3, but again, it is customary to write in this order. Minus 2 times I. This 2 gets multiplied by this minus 1. The result is minus 2. Minus I squared. On the next step, I will remember what is I squared. Plus, here I have 6, 2 times 3. Well, okay, let me write it probably 2 times 3. Plus 3 times 3i, this and this. Again, I put I to the end. 2 times 4i, this and this. And 12 times I squared. So this step is kind of trivial, automatic, nothing needs to be done. It is very easy. On the next step, well, I can multiply those numbers. That's very hard, but I'm able to do this. And I can turn I squared to minus 1. Then minus I squared becomes plus 1. Similarly here, I get 6 plus 9i plus 8i minus 12 because I squared gets turned to minus 1. Finally, I have to, well, sum everything together. So for the real part, I get 6 plus 1 plus 6 minus 12. And for the imaginary part, I get 3i minus 2i plus 9i plus 8i. Sorry. That is, here we get 1, and here we get a 18i. And that's it. This is the result. Please think carefully, everyone, whether you have any questions, because at this point, well, it is, if there is a question, it is better to deal with it at this point. Okay, very good.
And so we open the brackets in the usual way as we need.
Yes, nothing new because the distributive law allows us to open the brackets, and commutative laws of both addition and multiplication say that we can change the factors if we need, etc., etc. All the laws are the same as for the usual numbers. Thus, all the operations we already know how to do with usual numbers kind of immediately behave the same way. That's why we are interested in fields. Fields are the situation when everything works the same way as we already know. Okay, before we continue, let me now remind you one more piece from the lecture. That is the operation of conjugation. So it is called conjugation, or in full complex conjugation. In Russian, that is сопряжение. It is an operation that takes a number a plus bi. It is denoted by writing an overline above our number, and the result is a minus bi. So this operation is extremely simple.
So we in the end get conjugate.
Conjugate.
Conjugate. Sorry. I'm so mixed up.
Yeah. Yes. Yes. So a minus bi is conjugate to a plus bi. In Russian, сопряжен к такому-то числу.
So this operation just changed the sign
and nothing else. Yes.
Oh, okay.
Very simple and stupid operation, but we will need it. Okay, so for example, in this short exercise, if I compute this, I get 1 minus 3i. 1 plus 3i gets replaced by 1 minus 3i. And then I need to simply open the brackets one more time. I get the following. which equals 2 minus 3 minus 7i, that is minus 1 minus 7i. Please, once again, ask if there are any questions, because this moment is also very, very basic and crucial. If someone doesn't understand at this point, you will have problems later. We're going to spend 3 or 4 seminars on complex numbers, growing at each step, like doing more and more complex things with them.
Can you explain what we did after we opened the brackets? Yes, this
So
after that.
3i squared gets turned into minus 3. Well, and I simply add 2 and minus 3 together to get minus 1, and minus 6i with minus I together to get minus 7i.
Okay, thanks.
Again, you can kind of think that I is a constant, a fixed concrete number, but in some sense, you can think about I as it is a letter. You can do the same things you do with expressions with letters. The only difference is that for letters, if it would be x here, I couldn't simplify it any further. Well, I could replace this by 7, but I couldn't do anything with this part if it was x squared. But I is a special number for which I can simplify this part. That's good. In all the other aspects, it is the same as if it was some unknown. Okay, then we are kind of more or less experienced now. Let's go to a harder exercise where a new operation surfaces division. We have to divide now something by something.
But won't be this division be the same?
Well, the question is how to perform it, because in the usual division we kind of perform it well without much thinking. We already know how to, but here you will see that it is not obvious how to divide. So first, before we go to this, first let me multiply those two numbers. Again, that's easy, but one last opportunity to do some practice. So minus with minus gives plus, so 35 plus 6 is 41, and here we have minus 23i. So the question is how to divide.
We could, what we will do just the same thing as we divided like x, like 41 minus 23x divided by 3 plus x.
Well, okay, you could, but what exactly, I wonder, you do in those situations? I mean, when I have this, I usually say that, well, I can't simplify it.
Don't we need to?
Oh, but this is just some kind of rule, like to multiply. We just find the such number by which we'll get the higher.
Yeah,
like
so
33.
I can do it like this. For example, I can write that it is some, well, some number. I don't wish to compute it, but it is 41 minus or plus 23 times 3 divided by 3 plus x. But now this, so this part is okay, but this part I can't simplify it anymore. And here I will be able to simplify everything much better.
Don't we need to multiply and divide by conjugation?
Conjugate number. Conjugation is process, operation,
Yes,
сопряжение. Conjugate is сопряженный. So you are correct. So there is a trick. So similar to this, the situation, for example, when you had some roots, you can't divide directly, but there is a trick for multiplying both parts by, well, a conjugate number. In fact, there was a similar procedure of changing this minus into a plus. So here we do the same trick. Here we consider the conjugate number to this instead of 3 plus I, 3 minus I, and multiply both numerator and denominator by it. The result shouldn't change. But I claim now it will be easier to compute. Now, in the numerator, I have something not very good. That's life. But in the denominator, I have 3 squared minus I squared, which is very good. So it is 9 plus 1 minus I squared gets turned into plus 1. And here I have 123 minus 23 from this 23 times I squared. Minus 69I and minus 41I. That is 100 minus 110I divided by 10.
Can you send the link for chat?
Okay. Yes.
Thank you. So this part, so this can be now split into 2 parts in the obvious way, which equals 10 minus 11I. So I have simplified my expression to an algebraic form. I remind you that this form a plus bi is usually called the algebraic form of a complex number. And it is usually our goal to transform, to compute the number, and to simplify and simplify and simplify until it is in an algebraic form. The original expression was also some complex number. So in some sense, we could say, well, look, here it is. Look at this expression. It's the answer. But that's not compute the expression, right? Compute the expression is to simplify it until you get some algebraic form. Any questions here?
No questions. Thank you.
Anyone else? No questions yet? Then let me, well, like, emphasize one particular point. Here, I will introduce something in the denominator and obtain something like a difference of squares. What if it becomes 0? Is it possible or not? Because if we divide by 0, that's a problem.
Divide by 0I or what?
By just the number 0. What if the denominator becomes 0? What if everything cancels?
Oh,
That would be a problem. We don't want this. So does this problem happen or it doesn't? In this particular situation, this didn't happen. The denominator was 10, 10 is not 0. That's good. But maybe if we have some other numbers, maybe instead of 3 plus I, maybe something will cancel.
But no, I guess, because we actually get I squared is our minus 1, but when we try to multiply by conjugate, then we try to get this minus. So minus by minus will be always plus.
Very good. That's indeed the situation. So if you have some fraction where there is a plus bi, and so you multiply both parts by a minus bi, then here you get a squared minus bi squared, difference of squares, which becomes a squared plus b squared. Thus, it is non-zero if this number is not 0 itself. If we were not dividing by 0, which is, well, a forbidden situation,
then we are still not dividing by 0. So this operation is legal. Everything is okay. Is it understandable, or I need to have some?
Yeah, it's understandable.
Okay, sorry. Nothing works on my side. It was a stupid idea. Okay. Sorry, I missed a window and everything stopped working. Now it works. Okay, so, well, okay. So this, after this exercise, now we know how to divide complex numbers. So how to find inverses for each complex number. That's good. Each non-zero complex number. We can't divide by 0. That's good. Now, several more unconnected exercises. This exercise asks to solve a very simple equation. So,
Sorry for interrupting you.
Huh?
Could you again
return.
explain the last? Yes, yes. I think
Yeah.
I got it, but it's not really. So we can just add I where we want, or what? To make a sum. Yes.
What? I don't know what you mean, but sounds very naive at the moment. So maybe
I couldn't get the idea how we got a squared plus b squared. I mean, where we took I at first.
Here it is.
No. There.
Here it is.
Oh,
It
it's.
existed.
Oh, okay. Thanks.
I didn't invent anything new. Maybe this looks like the letter U, but it is B times I. Okay.
Oh, okay. Thanks.
Uh-huh. In fact, it looks a lot like U, but it's not it. Okay. So now consider the equation z squared equals -5. Can someone name? Yes.
So it don't have the I or something like that, or something like I number.
Yes, so its roots are similar to I in some sense, and the question is exactly, can someone name me what are the roots of this equation without any proof? Just give the correct answer first. Can someone guess which numbers satisfy this equation?
-5.
Minus
in the power of
-5 in the what? In the power what?
Maybe 4 minus
in the power -5 in the power half.
Well, that's very interesting, but that's just another way of saying, please solve this equation for me. This construction means this picture denotes the solution of this equation. So until we understand the solution, this is useless. The other voice, there was another idea. Someone else was talking and disappeared. Okay, any other ideas? Guys, it's easy.
No, I just was
We
thinking
need to
about maybe.
present this in the form a plus bi and multiply by it.
Very good. You are saying that we could replace z by unknowns a plus bi and find them. That's a good idea. Before we go there, maybe still we can just guess the answer.
It's like 5i squared.
Just 5i.
5i is a good guess, but when you square it,
5i
you get
squared.
-25.
No, just 5 and I squared without not power of everything.
Yeah, I'm sorry, but z is squared entirely.
Suppose this is
Square root of
this
5
is
by
square
I
root of
squared.
5 multiplied by I.
Okay, square root of 5 multiplied by I and minus square root of 5 multiplied by I both obviously satisfy this equation. I is used to obtain minus, and the square root is used to obtain 5. And there are two possibilities because this minus will cancel. What is not obvious is, well, we have found two such numbers. Maybe there are more such numbers. Maybe something else works.
The power is 2, so the number of roots is 2.
Yeah, there is a special theorem that the number of roots is no more than this power, but we haven't proved this theorem yet. So instead, let me work by brute force and use your suggestion to solve this, to simply find all possible numbers such that their square is minus 5. To do this, I open those brackets and I obtain the following. Now minus 5 is minus 5 plus 0i. It is a real number. Its imaginary part is 0. So if this number equals this number, then this part equals this part. Let me underline them. And separately, this part equals this part. Logic. And we are lucky this time. This particular system of two equations is easy to solve. We could be unlucky if it was not minus 5 here, but something more complicated, for example, 1 plus I. Then this method would fail because, well, here I would have 1 and here I would have 1, and I would have no idea how to solve this system of two equations. It is kind of a hard system of two equations because they are not linear. We don't know how to solve them. But this particular system is easy to solve. If product of two numbers is 0, then either one of those numbers is 0 or another one. Two options. Okay. Any questions here?
No.
So in the first, we obtain minus b squared equals minus 5 because a cancels. In the second, we obtain a squared equals minus 5 and b equals 0. So please look here, for example, we obtain the same equation we started with. Looks stupid, but the situation is different. Here in the original task, I assume that I'm asking you for complex numbers z. But here in this particular situation, now a is the real part of that complex number. So a is real. So this equation and this equation, they are different because this, like the set where we are looking for the roots of the equations is different. I hope this is easy to understand. So in fact, this system has no solutions because this equation is impossible to solve for real numbers. There are no solutions for this case, but the other case gives us the solutions. b equals plus minus square root of 5. I simply have to take the usual square root. I have a usual equation b squared equals plus 5, which I know how to solve in real numbers. And the result means that z equals plus minus square root of 5i, which is exactly what we obtained by guessing. Any questions to this task? Okay, then let me move on. And you might have seen the spoiler here. I have one more equation, and it is cubic. Does anyone know any solutions of this equation by heart? I mean, like, see any solutions? Yeah, don't
One.
hesitate. What?
One.
1. Very good. 1 cubed is 1. I hope everyone knows this. And in real numbers, this is the only number that satisfies this equation. However, I claim there are other complex numbers that also satisfy it. But it's not easy to guess them. I don't recommend trying to guess them. Instead, let's immediately do the same, well, procedure as last time. Let me write an unknown z in this form and open the brackets. The result is as follows. I hope everyone knows the binomial formula. The result is as follows, where this minus is because we have I squared turns into a minus. And this minus is because we have I cubed. So I squared gets turned into a minus and one copy of I remains. Okay, is this fine? On the other hand, 1 is 1 plus 0i. So we obtain once again a system. This part, the real part, let me underline it, equals 1, and the imaginary part equals 0. And again, the fact that we have 0 here allows me to split this into brackets and then do something clever. And if that were not possible, then we would have huge problems. But this time we may do it. Moreover, this bracket can be split further. Okay, I have invented some new form of a verb. Can be split further like this. Right? I hope this is clear. Thus, if the product of those three numbers equals 0, at least one of them equals 0. So we have three cases. Okay. And each of these cases we may solve. The first case is the easiest one, b equals 0, then a cubed equals 1. And a is a real number. We already discussed that this means that a equals 1. This means z is 1, a plus bi. That's the root we have guessed in the beginning, the simplest one. But we are interested in the other two, so let's continue. In this case, b equals square root of 3 times a. We can, from this equation, we can express b through a. Then I can put this into the first equation. I get a cubed minus 3a times square root of 3a squared equals 1. Here I have b equals minus square root of 3a, and and a similar equation. In fact, note that this minus, when I square it, it disappears. So this equation and this equation, they're the same equation. So I don't have to solve it 2 times. So if I open the brackets, I obtain a cubed minus 9a cubed equals 1. Which means that a cubed equals minus 1/8. And again, as a is a real number, we know how to solve this complicated equation. What is a equal to?
A equal to minus 1 divided by 2.
Thank you both. Very good. So we know a and b can be found using this formula. So in this case, it is minus square root of 3 over 2. And in this case, minuses cancel. It is plus square root of 3 over 2.
Thinking about the sign and cos of values when I
That's
see
true.
minus.
They look like cosines and sines. And next time we will discuss this in lots of details. But, well, in fact, they have their meaning as cosines and sines. But right now, we simply obtain 3 numbers. And it is a very good exercise. I heavily recommend you to take 2 or 3 minutes of your free time at some moment. Take one of those numbers, this one or this one, doesn't matter, and multiply it by itself by hand, like simply take and multiply it by itself 3 times. And check that somehow, I'm sorry, that somehow everything miraculously cancels and you obtain 1. It's very, what?
Sorry.
Yeah, it's very interesting to see how this happens, because when you look at a complicated expression like this, it is hard to believe that it is the square or the cubic root of 1.
I just consider when we will discuss this cube root from 1.
Yeah, we will discuss it in more details next time or even the time after the next.
See, I just about to keep every time thinking about it.
Okay.
That it's not actually 1.
Yeah, well, we will, again, it will be in the lecture and then in the seminar, etc. But right now, that is the end of what I want to talk about such equations. Again, more details later. If there are any questions about this particular equation, please do ask. Otherwise, we will continue. I have some more problems. Okay, so the last problem for today is this one, but it is quite big. So we have, again, we have a system of equations. The coefficients are now complex numbers, not real numbers. And the solutions might be also complex. Still, I claim that all the methods we know work perfectly fine. Nothing changes at all. That's, again, the power of the idea of a field. Field is something that behaves the same way as usual numbers. So you can do all the same things that we already know. So let me quickly solve this system by using Gaussian elimination. To do this, I will perform the step D, 1 divided by 1 plus a to the first line. I will divide the first row by 1 plus I, so that here I obtain 1. This is a classic move. Nothing surprising here. Well, here I obtain 1, but here I have a problem. I need to divide. So it is hard to divide complex numbers in your head. Usually we take some free space or maybe some like draft paper or something and divide them separately. Well, to divide, we need to multiply by the conjugate like this. So in the denominator, I obtain the sum of squares, 1 squared plus 1 squared, because this I means 1 times I. And here I obtain 1 minus 2I plus I squared. And 1 and I squared cancel. So I obtain minus 2I divided by 2, which is minus I. Okay, any questions for the first step?
No.
Now, well, my move is obvious. I use L to 1, which means use this element to cancel this. And the coefficient is minus 1 minus I, so that this part vanishes. So for this and this number, I again have to do some computations. So this number, we had 1 plus I, and we subtracted minus I multiplied by 1 minus I. We need to, well, compute this. So the result is 2 plus 2I, if I'm not mistaken. And for this number, I have the following. I had 1 plus 3I there originally, and now I subtract 1 multiplied by 1 minus I. So 1 cancels, and I get 4I. Like this. Is the second step clear? So basically, those are the same steps as I would have done for the usual system with real coefficients. The only difference is that each computation becomes slightly harder because, well, complex numbers kind of have more information inside them. So each elementary like operation with them, each step is harder. Well, that's life. Still, it's not extremely hard. Okay, then my next operation is D. I need to divide my second row by this number. So to obtain 1 here, then I need to compute what happens here. Oh, oops. Okay, let me still compute somewhere here. So I need to divide 4I by 2 plus 2I. Well, I can multiply by the conjugate. Again, if you have enough experience, this can be computed orally, but let's skip this and simply do it in the proper way. So here I have 8I minus 8I squared. Here I get 2 squared plus 2 squared. So this is 8 plus 8I. This is 8. So the result is 1 plus I. So I take it and put it into this cell. Okay. Now let me rewrite this matrix here on top. I won't perform any operation, just simply rewrite. And well, the next operation is obviously to add this row to this row with coefficient I to cancel this, to obtain the identity matrix on the left-hand side. Then the only thing that remains is to compute this coefficient. So this coefficient is 1 plus I times I, which is 1 plus I squared, which is I. And that's it. This system is in reduced row echelon form. So I can find that 1 equals I, that 2 equals 1 plus I. Hooray! Questions?
Could you get 2 examples back? I have question with the number where there was
2 steps back or 2 examples back?
2 examples.
So 2 problems back.
Yeah. Like, yeah, here.
Okay.
I just now don't realize why we decided to multiplicate I in the last step, where it comes from.
Not
I
multiplicate,
understand
but
the
multiply.
whole- Yes,
And
yes.
in this step,
Yes, where
well, in the very first step, I took Z and replaced it by A plus BI.
Yes, okay.
So Z is A plus BI.
Oh, okay.
So I take A plus BI, and here it is.
Okay, thanks. I
Very good.
just
Don't worry, it happens.
sorry.
Any questions about this task, maybe? Okay, well,
I suppose idea is simple.
yes, nothing really new. So I want to say 2 more things about this task. The first is that on the first step, there is a trick I want to show you so that, well, it might be helpful one day. Instead of dividing by 1 plus A, I could add this row to this row. What is the advantage? If I do it like this, then 1 plus A and 1 minus A, they add and I cancels. So the result will be 2. 2 is not 1. I wanted to obtain 1 in this cell. Instead, I obtained 2. But 2 is a number that is easy to divide by. It is easier to divide by 2 than to divide by 1 plus I. That's the idea. It helps to perform those first steps in a, well, in a more efficient way. But that's it. In this particular example, this idea won't help anymore. It is like a one-time trick. But in some exercises, such ideas might help sometimes to look whether it is possible to cancel something in your matrix by some clever operations before dividing. Because division is kind of, well, hard to perform with complex numbers. Okay? That's the first thing. The second thing I want to talk about is Cramer's rule. So let me quickly say that I can use Cramer's rule for this system. I can write my determinant delta like this. I take those 4 numbers and place them into a determinant. The result is this squared minus this squared, which is 1 squared plus 2i plus I squared minus 1 squared plus 2i minus I squared, which is 4i. I will not talk in length about all of this. I want to save some time, but still the idea is, I hope, clear. I can compute this sometime and I get the answer. Likewise, I can compute delta 1 I should put the right-hand side into the first column And I leave the second column as it was before and compute and something happens. And let me quickly look what was the answer with the other group, -4. Oh, sorry. Okay, I missed the button. Aha, now it doesn't
Happens.
work. But now it doesn't work. Okay. Let us return. So it was -4. And then Z1 is delta 1 divided by delta, which is -4 divided by 4i, which is -1 divided by I, which is I squared divided by I, which is I. Or alternatively, you can multiply by the conjugate here, like -1 multiplied by -I divided by I multiplied by -I. Still, either way, we can easily find Z1. You can then find delta 2 and Z2. I won't finish, but the idea is clear, I hope. Anything we studied that doesn't use square roots or something, that only uses basic operation, plus, minus, multiply by, and divide, anything can be used for any other field, including complex numbers.
So there we use the Cramer's rule.
Yes, so Cramer's rule, for example, can be used for any field, including complex numbers.
Well, so what what coefficient we try to find? I just missed. That's Z1.
Yes.
We just try to find the answer.
Yes, we find the answer using the Cramer's rule. Cramer's rule is a way how to find the solutions of the equation.
Yeah, I understand. I was mixed up for what we are trying to find by Cramer's rule.
Any other questions? Okay, then let me ask now everyone to switch on the cameras. And as I have hinted last time, we have a surprise quiz about determinants. It is quite easy. It is quite easy. Don't worry too much.
Is it okay that I'm in a cafe right now?
Sorry, what, Kat?
Is it okay that I'm in a cafe right now?
Well, okay, no problem. Well, I hope.
Just a moment.
Yeah, don't hurry too much, but don't be too late. So now the second thing is that let me divide you into two groups by the following rule. Those who have English nicknames, don't change the nicknames, will have the variant C. And those who have Russian nicknames will have variant D. I will send you the variants in a few moments. Oh, okay. Don't worry. They are quite equivalent. It is simply the way to divide you into two groups. Okay, let's wait for like a minute and I will send you the files.
I have some problems with the camera.
Okay, this happens. Try to solve them.
Okay.
Let me just say that it's nice to see you in, at least in this way. But, well, I hope we have offline at least after the new year. I hope, but last year it didn't happen. So
Yeah, 50-50.
something like that, yes. Okay, everyone has problems with the camera. That doesn't usually happen. Okay. So okay. Maybe I should have, I don't know, told beforehand. Okay, so семеро одного не ждут. So let's start maybe. So here are two files. Again, English nicknames, please choose the file C. Russian nicknames, please choose the file D. And well, I will send a link what to do with the results. Okay, it will be a Google form. There will be the task with true or false, like usual. For this task, there will be some questions in the form itself, like true or false, or I don't know. And for the other tasks, you just write on a piece of paper and photo it, as you do with many other tests, I think.
I'm
Okay.
sorry, I can't download it.
At all?
Is it my problem?
I don't know. What do you, you can't download the file? Okay. No, that's not your problem. If I send you a link to Dropbox, will you be able to open it? Okay, I will send.
Yeah, sure.
Let me. Oh, okay. I just think I have only now solved the problem with the camera.
Yeah, that's fine. On the exam, there will be more strict rules, but right now it is more to like imitate the idea that everyone is in the classroom, you know, like to make the atmosphere correct. So here is the variant C, maybe for those, if it didn't work like this, maybe it will work like this, okay? And here is the variant D.
So can I write my answers on the tablet or?
Yeah, you can use the tablet to write the answers. If you wish.
Okay.
And we have time till the end of the seminar or some less?
Yes, end of the seminar plus 2 more minutes because it took more time dealing with cameras than with the other group, which is not very good, but still. Okay, we'll see.
So I have sent the link for the form where to put the answers into the chat of Zoom. You can use it afterwards.
So we should download until the end of the lesson.
No, you should work until the end of the lesson plus 2 minutes, if you wish. So 4 more minutes. And then you can download, or you can do it right now if you're finished.
Okay, thank you.
I have a question. Is it okay that in the Google Forms that you send us, it is said that it's for group 213?
Okay, it was a misprint. I have fixed it. I obviously copied the form and I forgot.
Okay, if
to
I
change
send it by that, it's okay.
Everything works automatically, don't worry.
Okay.
On one hand, on another hand, I don't see a result. Ah, I see a result. Okay, it works.
Okay, I can go now, so thank you.
Yeah, and everyone who is finished, you can simply leave. No reason for everyone to say goodbye. We will be like overwhelmed. Just see you next week.
In the second task, can we just write the example of the cofactor, or we have to write it like
No, a definition, please. It can be in words or in formulas, but it should be a proper definition.
Okay.
Well, it is kind of time to finish, so please try to finish your thoughts and write down and send it.
So we have only 2 minutes to send.
No, again, you have no minutes to work and you have infinitely many minutes to send.
Okay. Thank you.
So please, everyone, finish writing and send everything. Well, not infinitely many, but like 10 minutes, 15 minutes is perfectly fine. Don't worry.
Okay, so
If you're finished, you're free to go.
So when we have to just upload it?
Again, already the time is already minus 1 minute left.
So can I still upload it, right?
Yes.
Okay.
Еще раз. Время писать закончилось, настало
Да.
время загружать. Время загружать, сколько вам потребуется времени. Сколько надо, столько, ну там 10-15 минут.
Я
Но вообще обычно за минуту выходит у всех.
Спасибо, у меня просто тут проблемы.
Бывает.
С перекидыванием файлов.
Перекидывайте.
Окей. Thank you. I can go now.
Yes, yes. Good luck, everyone.
Thank you.
Who is finished, you can go.
Bye.
thank you. Goodbye.
Yeah, I just have the scene upload, that is why it will take me a bit longer. I think first that I should mark it up answers for the first task in the form.
Yes.
I just did it.
Yeah, please just copy them into the form. It's not hard.
Okay.
I will be able then to check them in Excel without thinking.
I see.
Thank you, see you.
Thank you,
Thank
goodbye.
you. Bye.
Excuse me, do we have to send our work for the link? Because I just cannot sign in.
Давайте по-русски, я ничего не понял.
Давайте, хорошо. Я не могу в этот Dropbox зарегистрироваться.
Нет,
чтобы
Dropbox,
отправить.
нет. Ссылки на
Я все это
Dropbox
время
это...
сижу, значит, мучаюсь.
Да.
Так.
Ну, очень хорошо, если у вас будет Dropbox, он вам пригодится по жизни, возможно.
Спасибо.
А может нет, но... Да, это я просто отправил копии вот тех же PDF-ников для тех, у кого они не открылись.
Я поняла, куда
последняя ссылка
Так.
это Google формы.
Все, я вижу. Спасибо большое. Я последние 10 минут сижу, значит, пытаюсь. Спасибо.
Извините.
Ничего. Спасибо.
Dropbox — это такое облако, как Google
Да,
Диск.
я уже поняла, я не поняла, зачем туда. Ну, в общем, хорошо, сейчас я это все сделаю, извините, пожалуйста.
Ничего.
Я так понимаю, в Google форме, где yes, no, not true, yes, true, no, false.
Ну да. Ой, ну да, там же написано is it correct that или что-то такое, да, ну в общем.
Всё, хорошо, ну все тогда, спасибо, до свидания.
Успехов. Ой, 2000.
Я все, спасибо большое тогда, до свидания.